All right, let me do a sound check. All right, looks like it works. All right, we talked last time about uh, the concept. Let's see. I did switch computers this time, so I am on the apparently, seemingly, or philosophically slower machine, yet it's faster. Um, okay, so we talked last time about energy, and one of the things we talked about is this whole chapter is broken into two parts. The first part is and can include losses of energy, kind of like by friction. Essentially non-conservative. And then the second part of the whole thing is basically conservative. In other words, energy is conserved. Take a body, move it up, and you have potential energy, move it back down. But you can do this over and over, and there's no loss of energy in the process of moving it back and forth. So, hang on a second. Let me get my. Okay, so let's just pick up a problem. So, in other words, what I'm saying is section 1 here is more general than section 2. So I'm going to go ahead and pick up some problems off of section 1, and we're just going to work some of these. Um, okay. Um, let's see. Is there any loss of energy? Okay. Motor exerts. We did this one. Um, let's see about. Yeah. I mean that seems okay. Let's just do that one. I mean, these will get quite boring after a bit because. Okay, let's move over to start a new. Okay. Okay, so here in fact is the problem. A force of 250 newtons is applied to the end of B, which is right here. Determine the speed of the 10 kilogram block when it's moved 1.5 meters from the starting position. Again, let's just go through the whole sequence here. MGH, that's so what I'm going to do is I'm basically going to account for all the energy types, um, standard energy types, potential energy of moving an object up and down, the potential energy from a spring. There's not one there, but I'm basically doing accounting, so I'm basically including everything. Um, there might be several, and I'll put some. There may be several forces applied here. So I'm doing a sum because there may be some friction forces, there may be some other forces, and then I have possibility of having kinetic energy. Now, often you'll want to label these as a state 1 or a location and time 1 and 2 or A and B, but he already uses A and B to identify things here. So I'm going to this time, okay, so I'll do 2 and I'm sorry, oops, mistake, K delta 1 time 1. Hey, my handwriting's not that good here. Okay. Here's the 2, put a 1 and a 1. I'll say 1, 2, 2, 1, state 1 to state 2. And at this point, mgh1 plus 1/2 k delta, I'm sorry again, 2, haven't had my caffeine today, plus 1/2 mv2 squared. Okay, so let's start identifying things. Okay, first, started from rest. Okay, second, there is no springs. Now, the datum. Here's where you have to kind of make a decision. Okay, on this and this term, which is where I'm focusing, you have to pick a datum. Now, he's telling us that this kilogram block has moved, and we're going to make an assumption. Now, he's showing, now this is something we need to look at. He's giving us indication with this funny shadow here that it appears like block A is moving down. Let's determine if that's actually the case. Now, it could be that his picture is out of sync with his problem statement, but he's showing that there, which gives us that conclusion that that might be a case. But let's look at it in general. If you put 250 newtons down on this pulley, let's assume that right now we're not moving. We put 250 here, then that'll basically split this amongst these two and give you 125 and 125. Now this 125 goes up and finds this piece of steel and is attached up here. So it didn't really do much. This 125 goes around and holds this, and tensions this. So what we're saying here is, and here, let's go back to block A now. I'll go back to what we're saying in a second. I'm a little slow today. So here, you have, forgot, 10 kilograms. 10 kilograms times 9.81 gives me 98.1 newtons. So in fact, since this one is slightly bit larger than this one, then it appears to me like it's going to go up. Now, we're going to redo this. Well, we're not going to redo it right now though. Here, so, yeah, let's go ahead and do this right now. Okay, we've put 250 here, right? But let's do something else. Let's make it in general. Whoops. Now, we're just going to call it tension. Now that we know this is 98.1, I'm going to move it over. Now, over here will be legal And we'll go in and let's see if he uses the words to tell us. He does not tell us this, but we're going to make the assumption that essentially this pulley, this rope, all these ropes have no mass. So if you do a sum of the forces in the Y here, guess what? You get this being 125. And you get this being 125. Then you come back over and you get this being 125. So if you want to be legal, let's be legal. But my whole point in doing this wasn't to do this, although we can do this, and we might do this in a second. But my point was, is it going up? And we'll say it is going up. So I'm going to put my datum here, say this is state 1. On up here is state 2, and state 2 is 1. Okay, so this one's height is equal 1. Oh, okay, was it 1.5? 1.5. This one's height was equal to 0. That's all I was doing right there. But I'm going to go back and use this. That's why I'm not going to erase it right now. So this ends up being, okay, the mass is still 10, 9.81, and 0. Okay, we've got this force, which, believe it or not, is still 125. And guess what? Okay, so we're pulling it this way. This is the force here on it, some tension. It's moving in that direction. Since they're moving in the same direction, F dot X is equal to the magnitude of F, magnitude of X, times the cosine of the angle between them. Cosine between these two vectors is 0, which gives you nothing more than 1. Now, if they were going in opposite directions, meaning if you had friction, slowing and the object is moving this way, the force of friction times x, these are going opposite directions. Cosine 180 equal minus 1. So the dot product of this friction times the distance here it's moving is not minus the force of friction times however far it moved. The minus sign essentially tells you it's taken energy out of the system. Here, the force is making the system move. So it's positive. So in fact, you got 125, still 125. It moved that 1.5. And you didn't have any initial velocity. And you had no spring. So then you have, well, I almost said you had two terms, but this one isn't existing. So let's see. I'll bring out calculators and calculate that in a second. Okay. So let's zoom back in here. You want to know the speed of the block when it's moved, that far. Go back here. So it equals to, on this side, 10 times 9.81 times it moved up 1.5. Notice the theme here. It's keeping moving 1.5. That's what he told me right here. So it's 1.5. Now, the question is, it's still 10 kilograms. The question is, what's the final velocity? That's what you're shooting for. So all you're doing is taking this and this, 125, 1.5 minus 98.1 times 1.5. Notice something interesting here. And that is the 125 minus the 98 still exists, equals to 5 times v squared I guess at this point, let's see what I got as far as, okay. I'm going to have to, okay. Let's go ahead. Let this thing come up. Alright, it'll get there in a minute. Oh, maybe it has. Okay. 125 minus 98.1 gives you 26.9 times 1.5, because that's what you had here. Divide by 5. And then you got to take the square root of that. Two 2.84. So what I did is did this and ended up with that velocity. Now, here's the thing. Let's double check it. Here we're in. We finished this with energy, so we got an answer here. Now let's go back to our last chapter and say 98.1. Oh, sorry, 98.1. I told you I was a little off today. And this is 125. Doing it the old way. Sum of the forces in the y equal mass times acceleration. Whenever you find that acceleration, guess what? That acceleration is going to be constant. So, sum of the forces in the y, we're going to make this be positive. And 125 minus 98.1. I think that's still the... That's strange. My screen just popped up. Okay. Here. Okay. Okay, so that's still the 26.9. Okay. There you go again. Bright screen. I have no idea what's going on. Let me move. That's good for me. Okay, so 26.9 equals to, okay, that was mass times acceleration. The mass is still 10, acceleration, so acceleration becomes 2.69. Okay, now if the acceleration is constant, we have something interesting. We're going to just use S. S is equal to S naught plus V naught T plus acceleration I lost my train of thought. Acceleration T squared over 2. You also have V is equal to, V naught plus acceleration T. We know from what he told us that this is supposed to be, what did he say? 1.5. So we wanted a 1.5. Oh, by the way, this is 0 and that's 0. So that's 1.5. That's acceleration. That's T squared over 2. If I take that thing and stick it in there, and then, okay, 1.5 times 2, and then I got to take the 2.6, divide it by 2.69, then T, the amount of time it would take to get there, would be that. Okay, I'm hoping that my brain worked there. It may not have worked. Okay. So again, I'm just trying to check this. Nope, not 15. 1.5 times 2 divided by 2.69. And not only is my brain not working, neither is my 1.0561. 1.0561 is equal to the time it took to get there. Multiply that back times, okay, so now you're back in here and you want to find the velocity after 2.69 after so many seconds, those seconds being 1.0561, and you get, let's see, let me use the Alt key to do this. Okay, so if I do that times 2.69, was that right? Yeah, 2.84. So here, I got the velocity to be 2.84. Up, good luck. There, the velocity was 2.84. So as you can see, you got two different ways to work this problem. You know, this particular problem, I don't know. There's a little bit, if you look at the space taken here, this is a little bit larger than this. So I would vote for this one being a preferred way of solving it if you want to reduce the number of computations you have to do. Over here, you had to find the time it took to move that 1.5 meters. Put that back in the constant. Okay, so what you had is these two equations that were constant acceleration equations. You had to use them both. So, in any case, that's just to show you how you can use either one. Now, let's see if we can find another interesting. Okay, so all right, here's one. So let's see if I can just. I used to have to use. I need to use all fingers there. All right. New page over here. Okay, yep, I know I've copied you. Okay, this time it's a little bigger. Okay, so the force of 50 newtons is applied to the cord when S is equal to 2 meters. If the 6 kilogram collar is originally at rest, determine its velocity when it's made its way right back to here. Again, if I just write the equations blindly, now again, this force could be an applied force or it could be a friction force. Okay, and if you think about it, an applied force might be in the direction of motion. Usually it can help the motion. A friction force would be in the opposite direction of motion, meaning that the sign would change to a negative. Okay, now I have to put the kinetic energy, mv squared, and excuse me, mgh plus 1/2 delta x squared, and there may be other terms that are used here, plus 1/2, oops, yeah, 1/2 mv squared. I'll say this is state 2. I'll say this is state 1. One of the things I notice is I'm always going through the assumption that gravity goes in this direction. This block can move all at once back and forth. It hasn't moved its datum. So these two terms equal each other, and if you put your datum right there where it's at, they're basically 0. Second thing is there are no springs here. Speaking of that, I probably need to do a spring problem in a minute. And he says it's originally at rest. So this is gone. So what I actually have is f dot x from state 1 to state 2 is equal to 1/2 mv squared. That's it. Now, this is that same concept. Okay, he told you that this is 2 meters over. So if you want to know the distance, and we're going to assume this is a big point here. So if we want to know the distance or the length of this rope from here to here, it's just 1.5 squared plus 2 squared, and that should be equal to 2.5. Let's double check that, make sure it is. Okay, so square root of 1.5 squared plus 2 squared, 2.5. The reason I knew that is because if I multiply this times 2, I get 4. Multiply that times 2, I get 3. And that's a 3, 4, 5. So that's 5. And I can take that 5 and divide it by 2. That would give me a 2.5. So the length of that rope initially is 2.5. When this collar is drawn all the way against here, the length of this rope is 1.5. So the rope itself, or if I spray paint or put a piece of tape right here, this piece of tape moved the final state. Okay, so state 1, state 2, the total distance it moved was 2.5 minus 1.5, or just 1. Again, what happened is I can put a piece of tape or paint the rope right here. This would have rolled over. If this diameter of this pulley was 0, it would have rolled over and moved out here a distance of 1 meter. So the F I applied is 50 newtons being pulled this way on the rope, which it moved in that direction. So I'm pulling the rope in the direction it's moving. Dot product here positive. 50 times 1 equal 1/2 m. What was the m of this thing? 6 kilograms times v squared. So v would equal to 100 divided by 6 in the square root. Take the 2, hit the 50, gives you 100. Take the 6, put on bottom, and that's pretty much it. Now comes a fun and interesting thing. Now, let's assume for fun and our own enjoyment, we're going to do the thing using F is equal to MA. We're going to assume this to be positive, and let's make it at least a little easy on us. Let's assume this to be positive. Okay, so now we have this being pulled here, and it's being pulled at an angle. Now, how far do we move? How far does this block move? It moves from where it's at over 2 meters. But here's our problem. Okay, now we have a force component going this direction. That's a normal. It's offset here. There is no friction force. So we only have to deal with the sum of the forces in the x direction here. But we have a component here. This force being applied is equal to the total force, which guess what? The total force is still 50. 50 times the cosine of the angle. Now, the cosine of that angle, here we're gonna work on this in a second. The cosine of that angle, what happens after a few seconds, or however, milliseconds or whatever, the angle changed. And eventually, the angle is going perfectly vertical. So here's the problem. I get 50 cosine of an angle is equal to, what was the thing? It was a 6 kilogram block. 6 kilogram block times the acceleration. Angle changes with time. Acceleration changes with time. It's not constant. How do we deal with this? Well, there's a couple ways you can do it. And you can start seeing why that the energy methods are so wonderful here, because now I've got to figure out how to work my way through this to find this. So I have an acceleration which is a function of the position here. When I'm right here, the acceleration's equal to 0. So I could go in and say, and let's do this way. Okay, let me go ahead and do this in a generic sense. This is going to be s squared plus 1.5 squared. Whoops. Now, cosine of theta is equal to, okay, and this is the theta, so that's the theta, would be s over square root of s squared plus 1.5 squared. So I would get 50 divided by 6, or what is that? And I'm not going to go all the way through this because it's kind of a waste of time. 8.33 s over square root of s squared plus 1.5 squared equals to the acceleration. Now, ordinarily, I might say, here's an interesting approach. I should say that if I want to get down into the velocities, because actually he wants to know his velocity when he gets there. So I can just step it down one step and get to the velocity, right? However, this is the case, right? Oh, but wait a minute. Acceleration is not listed. In other words, if I did this, oops, sorry, I'm thinking one step ahead. If I look at this, this implies I need to do this to integrate. I don't have that. So what I have to do is I have to say, well, shoot. I have to use the chain rule. V dv ds equal acceleration. Move that over. Now I can integrate this. V dv. Integrate this. On the right hand side, guess what I get? V squared over 2. Hey, wait a minute. Let's take a look here. I get a V squared here. I had a V squared there. Now that's starting to look very familiar. But guess what I got to do? And this is the part where I may just give up because I don't want to go any further. S over square root of s squared plus 1.5 squared ds, I'm cramping it, so let me rewrite that. Maybe I'll rewrite it backwards. There you go. Equals to ds of s over square root of s squared plus 1.5 squared times, Oh, all right. I'll put 50 back over 6. That's what that is. And then I integrate. Okay. If you love integration and you want to go this route, I think that's great. I'm going to let you do that and prove the rest. But where would you integrate this to? Now, I've already, you have to realize he's picked the S going this way. I've picked it going the other way as being positive. So your limits probably should be 0 to 2. I don't know. Do I feel like doing this? No, I don't feel like doing this. But if you carry this out, of course, the first thing you're going to see is the fact that on the right hand side you get a square root, and the fact that on the right hand side over here you got the square root, and you got that 1/2, means on the left side you will end up with a square root. In other words, what I'm saying is the answer is going to be 2 times the integral from 0 to 2 of 50 over 6 s over s squared plus 1.5 squared ds, and the square root is going to be v squared. My point in doing all this is now let's look at the workflow. Okay, it is true that here my handwriting was a little larger, but I'm not even done yet. I got to do some more integration and then substitution and stuff like that compared to the amount of work it took to do that. This is the beauty of energy methods. Here, it's a circumstance that it's kind of doable. There are many times that there are problems that are not even doable with this method that are doable with energy methods. Let me give you a case in point. You have a, and then I'm a, what time is it? I do not see the time anywhere. I have my cell phone, 36. So I can do this and call it quits. Let's say we had something like this. Okay, for those of you who might be in physics, I can't figure out why I can't get it to go to the right. So let's say you had a truck, and the truck was moving that way and slowed down and did some sort of funny motion. In the truck, you had a funny shaped bowl or a pipe. Let's say you had a pipe that could roll. So this is not, anyway, get rid of that line in your mind. The pipe can roll back and forth, but inside that pipe is another pipe, and that pipe is another pipe, solid steel pipe. These are all moving. This one can roll back and forth on this. This one can roll back and forth, and this one can roll in there. Good luck doing some of the forces equal mass times acceleration there, but there's a method called Lagrange equations, and it's an energy type method in which if you can do the coordinate systems to this particular problem, you can actually solve that and solve it as a function of time. So you can actually then start plotting the motion of this moving back and forth and things like that. But we're not doing that in this course. Let me go back to the book. And I think at this point, I'll go back to the problem sets next time and look at those. But I think all of these problems are fairly simplistic to do. All you got to do is set up the energy equation on the left, energy equation on the right, and include the term of energy from state 1 to 2, and you just fill them in. You identify the energy as states, and that's it. There's nothing more. These are very simple. Okay, here's your spring. I guess I should have done a spring problem. I'll do a spring problem next time in class. And for right now, I may call this good because there's not enough time to do up another problem, and we'll just go on from here.